Thank you for this opportunity. First, I want to introduce myself. I am an applied physicist at CERN, the European Organization on Nuclear Research, which you may have known that our flagship project is the Large Hadron Collider. I have been, for the last 17, 20 years, leading several development projects on software to provide common software to the experiments, not only at CERN but elsewhere. And at the beginning, 20 years ago, I was one of the first to introduce Python to combine with C++ to make it easy for whatever configuration, analysis, and so on and so forth. So you may know that high-energy physics experiments consume a large amount of computing resources, in particular on the simulation, which is the topic of this presentation, but also in reconstruction, and there is Graham's talk in 1 hour from now, and on data analysis. Speed is very important. Therefore, we use C++ in most of the places, but also the ease of use is also very important. And the community has developed ways to deal with these two language problems of C++ and Python, but certainly we pay a price. Now, we want to evaluate if Julia really can help us on this problem. And one way of doing that is, one of the important things that we need to assess is the interoperability with existing C++ libraries. Okay, the community has been developing for many years, millions of lines of code. In total, perhaps there are 40 or 50 million lines of code, and certainly you cannot start from scratch. This is not feasible. So in this evaluation, one example that I have been working on is this Geant4. I'm going to introduce in a second. This is a simulation framework, which is extensive, is very complex, and is very challenging to rewrite, and is used by basically all the experiments and more. So the outcome of this evaluation will be to introduce these new functionalities in Geant4, and which perhaps this will be an add-on to the existing C++ code to make it more accessible to potential users which have perhaps somehow limited C++ experience. So Geant4 is a simulation toolkit for simulation of passage of elementary particles through matter. You take particles, electrons, gamma, whatever, and you do step by step the interaction of this particle with the atoms, with the nucleus that it finds. Okay, so it combines many models following the full range of energies on the different models that will interact these particles with the matter. Particles will produce secondaries, and then you track these secondaries, and so on and so forth. So it's a very lengthy process, and you collect all this information during this tracking. Now, this is primarily used on the fields of high-energy physics, on nuclear physics, on the medical, on space science, and many other things. Okay, whatever you need to understand what's going on with some radiation or some particles interacting with the material, you can use this toolkit. It's developed in a large international collaboration, the Geant4 collaboration, and is an open source license over more than 2 million lines of code of C++, and has been developed for more than 25 years, so it's a rather complex piece of software. Now, the way I handle that is that I want to wrap the C++, and I want to make it available to Julia. For that, I have been using this package, cxxwrap.jl, which basically it works like the Python PyBind. Okay, I don't understand. It works like PyBind or 11 or Boost.Python, that basically you need to write a couple of lines of code for each of the methods that you want to provide to C++. Thanks to this package called Rapid, which is developed by Philippe Gras, makes use of the LLVM to understand the C++ classes and generate these 3 or 4 lines of code per method automatically. So that really helps a lot on producing that. And it also helps a lot on the sustainability in the long term, because new versions of Geant4 will be happening basically every 6 months or 1 year. So it's nice to have a mechanism by which you can incorporate the changes in a less effort manner. So the basic, once you have done that, the basic interface is quite straightforward. It looks like a Julia thing, or you just say using Geant4, you just instantiate the objects that you want there. For the people that are not used to Julia, it makes a bit different that you don't have methods of function. The method does not exist. You have to pass the object as the first argument into the function, but that's really you learn very quickly. All the classes of Geant4 are prefixed by G4, which makes very nice because you can export all of them. There is no conflicts with other types that will be fine, or very likely not many conflicts. So you can just use it and so on and so forth. Okay, that's quite straightforward. What considers the package structure, what we have achieved here is that the Geant4 package is really a purely Julia package. And everything that has to do with the binary code, this is done in _GLL packages, which has been produced with the binary builder. And then all the different artifacts for the different architectures and platforms has been available there, and then automatically, transparently by the user, they are loaded. So that's really great. It works very easily from the basic flavors, Linux, Mac OS, and Windows, which certainly is an advantage. It's an advantage really for people that wants to use this toolkit, and they just do a package add, and that they get everything that it requires. Basically, the way this is done in the C++, user has to inherit from a base class, which then you declare it, which then the framework, the toolkit will call you, okay? But in Julia, you don't have inheritance, you don't have methods, you don't have this thing. So what I do simply is to provide functions there. And to provide functions like is shown here, that I don't see my mouse, but okay. You provide functions like in this case a step action that you will provide some instruction on the Geant4 toolkit, which represent a step, and you provide some reference onto something that from where you can get all the rest of information, okay? Something like represents the full application. And then in here, you just extract the information you want. On that step, what was the energy that I got? What is the position of this step? What is the next? Which is the direction, and so on and so forth. Whatever you want to extract, you can have it there. Now, multi-threading, I mentioned that Geant4 provides multi-threading in there, that it is able to process each collision or each event in parallel. So that's it's a trivial parallelization, because each event or each set of particles are independent, so you can really develop that in parallel, and it has a very, very good scaling. Thanks to the threads are managed by the toolkit, but thanks to the foreign thread adoption that was introduced in 1.11, this is now possible that the threads are in Geant4, but these are calling functions from Julia. Okay, so that works nicely. The only detail you have to make sure is that each of these user actions are being called by several threads. So you have to worry about data races there, okay? So basically the trick here is that you duplicate the storage of the data that you have there, and each thread will be filling his own set of data, and then you merge at the end. You do the reduction. So user actions I mentioned already. It's nothing special. It's just Julia functions that get some from the arguments. You get the information you want. There is no globals, okay? And there is a way to get your own copy of the data that you want to fill with counters or histograms or you name it, okay, with some data frames or if you want to collect information. So that's typically for each application, you define what I call the simulation data, which will be the result of my application. The result of my application typically will be counters, some vectors of information, or some histograms, or some data frame, or something like that, and then you provide a reduce function to add all of them at the end of the run. And finally, you put all these things together. Okay, you put all these things together in what is a Geant4.jl application, where you put the detector geometry description, you put what physics you want, you put what is your particle generator, initial particle generator, how many threads you want to run, what are my actions, and basically you create an instance of that thing, you configure, you initialize, and you run. And then you can extract the information out of the thing. So nice. Once you have it in Julia, then you can also start using the bits and pieces of the Julia ecosystem there. And in that particular case, it was very easy to visualize the geometry and visualize the particles that you are producing on this during the simulation using, for instance, Mackie, including Boolean solids with this IGL package that is able to combine shapes and make Boolean operations with them. And at the same time, you have very interactive things in there. So how it will look like a full example in there, a full application is something that will take 100 lines long. Okay, it's nothing really exceptional. You define you define your simulation data, you define your geometry, and basically you combine together and you make one of these instances of this application with everything. Okay, basically, as I said, with what data I have, what the number of threads, the physics, the actions, and so on and so forth. And then in the same application, you can then use data visualization tools or analysis tools, and you can collect. And this is certainly an advantage with respect to the Geant4 in C++, which is combining other things on C++ is possible, but it's not easy. Okay, that to do the simulation and at the same time the data I have collected to do some analysis with it and some visualization of it. Like in this example I'm doing, this is like a sampling calorimeter that you shoot some particles, and then you see the energy deposition in each of the layers of this calorimeter. So, and with Julia, as I mentioned, also it comes interactivity for free, which is great. It's great for developing your applications. You can develop your user actions and see what if you are doing correctly, and you with a revise module you can change things, you can see what's going on. The same thing with notebooks. You can see the geometry, you can see your detector, you can see how you are building up the detector, and visually you check that it makes really sense and you didn't inverted the transformation and things don't fit anymore, and so on and so forth. And at the end, okay, everything is very well integrated on VS Code, on IDEs in there, which is great. Now you could ask yourself, what is the performance? Are we losing anything on doing that? And the answer is no. Obviously, the main number crunching is still in C++. The only thing that you offer is a Julia interface to the C++. So the performance should be equivalent to the C++ application. And in reality, it is like this, okay? If you run exactly the same example in the Geant4 toolkit, there is some basic example number 2. You can run it in both cases, and you can see that you get basically the same, except that the Julia is slightly longer on a startup, okay? But we know about that. And if you run it for one event, one takes less than a second to initialize, and and to produce one event, while the Julia case, it takes 6 seconds. But okay, since you typically run for hundreds, thousands, millions of events, because what you want is to really have high statistics, at the end of the day, you see the same performance. And then when you apply some multi-threading in there, you get the same scaling, because at the end of the day, the threads are running on the C++ pool, okay, of threads. Conclusions of this work. I mean, this package, the Geant4.jl, allows people to develop simulation applications without the need to program in C++. The installation and the portability among the different major platforms is trivial. It really is very straightforward. You get a much higher level and friendly, at least this is what I think, a friendly user API. I mean, just counting the number of lines is you divide by 10 the number of lines that you have to write, typically on a small application. And also you have a very nice built-in tooling and ecosystem, which is very complete, and you can really exploit that. And the capabilities and the performance, it will be identical to the C++, because at the end of the day, as I said, you just call the C++. It's nothing special. We are not changing any physics model or anything here, okay? And the same capabilities, you will have it in one side and the other. And at the end of the day, is also, even if this evaluation, I think the conclusion is very positive, depending on where we go later in the physics, on the high energy physics, okay? And but nevertheless, this is a good add-on to the Geant4 project itself, because it provides yet another set of bindings on a language that will allow you to be very productive and without the need of learning C++. That for our domain on high energy physics is not a problem, because most of the people working in our field know C++, but in other domains like medical physics and things like that, this is not as easy, okay, typically. And then it comes with the rest of the ecosystem on Julia, which it could be very nice for visualization, data analysis, and so on and so forth. The thing is, in a working state, and functionality can be added, because I didn't wrap all the 2,000 classes that are in Geant4. I only wrapped the ones that you interact with it. But okay, it could be that for certain cases you need to interact with other classes, and then it's very easy. You just turn the handle and can be added. If you want to try out, there is a set of Jupyter notebooks as a tutorial, which tells you step by step how to build a full simulation application, and includes a number of complete examples in there, which is quite nice. And then I finish with a bit of an announcement. We at CERN, we are organizing a Julia HEP workshop at the end of September, October, beginning of October, which, okay, you are most welcome to participate if you wish.
Thank you very much. Any questions? Okay, we have one there.
The latency difference that you showed between the C++ and Julia can be reduced by precompiling the workload in the Julia package?
Probably, yes, probably, yeah. But I didn't worry. I was not worried too much. Okay, it's a few seconds. Taking into account that there are, I think it's written somewhere. I think I did more than 200 classes with the methods. I think, yeah. I'm wrapping almost 3,000 methods, okay, which is quite a lot. And of course, you don't use the 3,000 methods, but since this is automatic, you say, I want to wrap this class, and this class comes with 20, you just wrap the 20, okay? It's done. But you see, there is a lot of things, and it really doesn't take very long to load, okay? And in addition, understanding that there is all these binary packages behind that it has also to be activated.
Thanks.
I have a kind of a comment. I think from the advertisement point of view, the example to benchmark on would be nicer to have also the next layer, the visualization or some sort of data analysis, and then you could compare the efficiency of the whole system, like not just a wrapper, because this is what you are showing, but also, for example, if I use a Python wrapper to Geant4, how long it takes to run the simulation, analyze the data, and make a plot. So then there would be some differences more visible, I would say, from one to another.
Yeah. Concerning the Python, there is a Python bindings for Geant4, but at the end of the day, they are not useful. Not useful because if you write your user actions in Python, and this is called every step for every particle, the overhead is terrible. Okay, you can do perhaps simple things, but if you want to do some more complicated thing on the user actions, it's completely useless. It's impractical. Okay? It's practical for the configuration part and all that, but it's impractical to run a big simulation with that. Now, and also for visualization and yes, Geant4 comes with some predefined visualization, but here you are much flexible, okay? Because the visualization is so simple with these interfaces to Mackie and things like that. You can say, look, I don't want that to draw these things in this way. I want to draw it differently, okay? And then it becomes trivial. For instance, I did this example here, like represents a bubble chamber, and I said I want to show the particles. I want also to put the labels, okay? I mean, Geant4 doesn't do that, put the label, but to put the labels there was one line that I had to change, okay? So it gives you much more flexibility than what you have currently on the current system, because it's trivial. But okay, you can do something like that, okay? But at the end of the day, this visualization, you don't run big productions with a visualization on. This is basically to debug your application, okay? You want to make sure that the geometry is what you think, and you want to make sure that the physics you are showing there is what you think, okay? And then once you have it, you switch off visualization and you run for a million.
Thank you very much. Do we have other questions?
If I want to learn, if I want to learn Geant4 now without prior knowledge, is it possible to do that with this package? Or?
Yeah.
Ah, nice.
Yeah, of course. The details, the details of what each model does and what physics behind and things like that. There is pointers to the original C++ documentation. Okay, but yes, you can if you follow the tutorial, there are pointers there that will show you the really, if you want to interested in the details of each of the models, basically.
Okay, thank you very much. First question.
Yeah, very short question. If you're updating something like major on the C++ side, like you add a whole new feature, is there not a lot of maintenance then to also?
No, because
you use Rapid?
Yeah, because I use Rapid. You will have to, basically the input to this tool Rapid is basically a list of header files, and then all the classes that are found in these header files will be automatically Rapid. So if you are adding a new physics model with different, yes, you will have to add one line onto this input, and then you generate the thing, and then you can use it. Okay, modulo, yes, but it's trivial in the sense that it doesn't require a lot of coding. Okay, it's only to configure this input and to regenerate the wrapper.
Okay, thank you very much. Let's thank again Pere Mato